Hello, this is Concrete Path. Today, our new lecture would be that's called as transformation of stresses. So we'll be deriving that equation also, those equations on the transformation of stresses. Let's go and get those stresses. Transformation of stresses. Transformation of stresses. So when we say that, stress, shear stress or normal stress, stress is a tensor quantity. You might be knowing that stress is a tensor quantity. That means it needs magnitude, it needs some direction, and a plane on which it's acting. So for this case, we have the plane. That's very important. On what plane your stress is acting, that's very critical. So let's say you have a general beam. Then we say that we take some point or any section, we say moments about that point, summation of moments about that point equals to 0, that point P. That means we only not say that particular point should be in equilibrium. We say that the entire section or entire volume of the beam, each and every point should be in equilibrium. Each and every point should be in equilibrium. We don't only say that each and every point, say these are some points, these one, this one, this one, this one, this one, this one. We don't say that only it should be in equilibrium. We only say, we say extra. The main point here is we say that every point it should have stresses, shear and normal stresses, that should be less than the permissible stresses. So we can say you apply some loads. Because of the loads should be such that which should not create stresses in the stresses in that point material greater than, that should not be greater than the stresses it can bear, that's its strength. We can say stresses should not be greater than that strength of that particular point of the material. So this is the constant. Then you should get to know that what is the maximum stress it can bear, how much stress it can take or it can develop. So you are applying load, because of that stress is getting developed. So if the load is such that it exceeds the stress bearing or load bearing capability, so we say that it has the load has created stress that is greater than the strength of the material. So we need to say on what particular plane, because stress is a function of plane. We can say stress is a function of plane or theta. So it depends on the orientation of particular plane. On that plane, the stress can be anything. So we need to get on what particular plane the stress value is maximum. So that's why this concept of that stress transformation is there. Let's say your our point is there. We take any point. Let's say we take any point. Let's say this is point A. We take any point A, and we want to see what's happening in this point. We would say there are some infinite number of planes passing through this point. Infinite number of planes passing through this point. So on what particular plane the stress is maximum, or on what plane shear stress is maximum, normal stress is maximum. Let's say you take one plane. On that plane, some sigma is there, that's let's say 10 megapascal, and tau is there, let's say 8 megapascal. Similarly, you take one more plane, arbitrary plane. Let's say here the sigma is now from this study you say that let's design the material for tau of 10. We can say shear strength of tau. We can say, let's say the shear strength is, let's say the material, let's select the material whose design shear strength is 10 megapascal and whose this normal strength we can say that's strength for the normal stresses, we can say sigma strength equals to, let's take 15 megapascal. Now, now you see that you have designed the material with respect to this plane. You have designed the material with respect to this plane. But if I say add any particular plane, let's take this plane now. If I say what's the value of stress here, let's say the tau is 2 megapascal only, but sigma is somewhat equal to 18 megapascal. So your material can fail here because your stresses had developed greater than 15 megapascal. The material you have provided that its strength is 15, so but the stress is developed on this particular plane, on the particular same element, same point of the material. It is having different strength, different stress value along different planes. So by varying the plane at a particular point of the material itself, your stress varies, stress value changes. So we can say your transformation of stress means that means, let's say you have bar, that stress we're applying a horizontal load of that tensile load of px, and in the vertical direction we know stress would be 0 because you are no load, you are not applying any load in the y direction. So we can say stress in y is 0, but stress in the x is some value. So stress transformation means that that on a particular plane you are applying this is your particular plane, let's say you are applying a stress of px. So then stress becomes sigma x. You are applying a stress of sigma x on this particular plane, and sigma here 0 in the y direction, so you are applying a sigma x here. So you want to say, by knowing stresses on a particular plane, on one plane, but you want to say what is its effect on all other infinite number of planes, infinite minus 1 or infinite minus 2 planes. What's happening to those planes? What is the effect? How much stress has been developed on other planes because of the stress that has developed on the particular plane that you analyzed for. So that's how transformation of stress works. Say, if I say general loading case, that general state of stress, that this is a point, there is some sigma x in the sigma y in the y direction, this is y direction, this is x direction, and this is z. So we can say in the z x y and in the x direction there is some sigma x acting, in the y there is some sigma y, there is sigma z acting in the z direction. So similarly there is some tau associated along the plane xy, tau xy, here also tau xy, and it's in this plane we have tau xz, or we can say tau zx. It depends on the particular plane. So there's some tau and there is some sigma associated with each plane. We know that one plane carries one normal stress and two shear stresses. Similarly, if you have three planes, we can make it a we can show it by a cuboid. That's how that particular point is represented by state of stress. So to represent the state of stress on that particular element, you can't show that this is point, here is sigma x, sigma y. It becomes invisible. To make it visible to our eyes, we say that let's make it a cuboid, and say on different faces of this cubic element we are applying those stresses. That's we call it as a stress element. Let's name it as a stress element. We call it as a stress element. That point, it shows the point that that particular point is acted upon by some stresses along different directions, some sigma and tau. So if I represent that, there is some sigma y, and this is sigma x. So along the outside the plane, that's sigma z, and there's some shear stress associated with those planes. Let's say this plane, this is which plane? This is z and x. This is xz plane. So if I apply shear stress in this direction, I can say draw the outward normal to that. That means it's acting in tau x and the direction of the arrow, it's in the z direction, so I can say tau x z. So if I say what's that, what is the stress value of this one, how should I represent this one? So I can say draw the outward normal, so it is stress in the y, shear stress in the y, and direction is in the x, so I can write tau yx. Similarly, if I write what's the direction of this one, what's the value of, how should I note represent this one? I would say draw the outward normal, that's tau x, and it is in the direction of z, so I can write tau xz. Similarly, if I write what should be the stress representation of this one, let's say this one. So I would write it's acting downward, so outward normal is outward, so tau y, and direction is in the z, tau yz. So if when we represent the stress matrix, that are tau ij, that's representing those elements, so that state of stress for that particular point. So I would say this is tau, that is tau ij, that's stress, sigma x, that's sigma y, and sigma z. Because this is symmetric about the main diagonal, we know that this is tau xy and tau xz, and because of that concept of complementary shear stress is that tau yx equals to tau xy, so we can write tau xy, tau yx. Similarly, tau xz equals to tau zx, and tau yz equals to tau zy. So because of those, out of those 9, you have 6 independent stresses you need to get in order to define the state of stress of that particular element. But that's very calculation that would take a lot of calculations. But so our syllabus is restrained to that. We call that as plane stress condition. That means you are applying stresses only in a one particular plane stress condition. That means your sigma z, we say that sigma z is 0, tau xz is 0, and tau yz is also 0. So if I represent that element, I would say that this is sigma x, this is sigma y. So this is tau xy, this is tau xy, this is tau yx, this is tau xy, and this is tau yx. So if we see that out of those 6 faces of the cube, we can say this element, this face, and that the last face also, that the 2 faces we are having, that 2 faces are without stresses. We can say 2 faces are stress free. 2 faces are stress free. So we call it as also that it is a condition that 2D stress and 3D strain condition. That means you are not applying stress in third direction. That means you are applying stresses only in sigma x and sigma y, and tau xy, but you are not applying sigma z. But the strain developed because of the Poisson ratio. We know that Poisson ratio, strain in z equals to sigma z by e minus mu sigma x by e minus mu sigma y by e. If the sigma z is 0, okay, but the effect of that Poisson ratio would be there. Strain in z is not 0. See, so the plane stress condition means you can have plane stress condition means tau z must be 0. It must be 0. Tau xz must be 0. And tau zy must be 0. These 3 you have to ensure that it is must. But for the other 3 cases, that's tau x, sigma y, and tau xy, they may be 0 or they may not be 0. That's what is plane stress mean. You don't have to say these should be there. Tau x, sigma x can be there or it can't be there. Sigma y can be there or it can't be there. Tau xy can be there or it can't be there. So you have to say that must condition is that these 3 you have to ensure for the plane stress condition. So we are focusing on that plane stress condition. Let's take that plane stress condition now. We are saying, let's say we are focusing on that plane stress condition now. This is our element. This is our element. Let's take this as our element. So now there is the derivation you can write. Sorry. You can write the derivation of stress transformation. Stress transformation. Let's say you are applying a stress in the x direction, sigma x, and you are applying also sigma y, but you are not applying sigma z. That's what plane stress condition is. So you are applying also shear stress tau x by tau yx. So if we represent it by a plane, particular plane, let's first analyze that how it is possible that. So there is some shaft, we call it as a shaft. So you apply a torque. In that particular this scenario, there is no shear stress. If I select at any particular point, in that point there is no sigma is 0, sigma x is 0, sigma y is 0, sigma z is 0. So only shear stress is acting in this point. Only tau is acting because of the torque, or that shear stress is developed, and only shear stress is developed, no sigma is developed because of this torque. We say that this is pure shear case. So it is a condition that we can say it's a plane stress condition. Why plane stress condition? Because sigma z is 0, tau x z is 0, and tau y z is 0. And apart from that, your sigma x and sigma y is also 0, but that's not our issue here. We can say it's a plane stress condition because from sigma x, sigma y, sigma z, that tau x y, they can be 0, they can't be 0. Okay, this is your pure shear. That pure shear case, it's also a pure that plane stress condition. Similarly, you can have that simple tensile load you applied on a bar in the universal testing machine. You applied a load of P. Let's say that P by A, that's equals to sigma in x, and we know that here we have only sigma x. Sigma x is not 0, but sigma y is 0. Sigma that tau xy is also 0. But must condition is that if tau xy, tau xz, and sigma z is 0, then we can say this is plane stress condition also. So similarly, once you got, say this was a particular plane, once you got on this particular plane, only sigma is acting, sigma x is acting. So we can say we know that from that we can say let's assume that general case, that 2D general case, that plane stress condition. That's our plane stress condition, that only sigma x is acting, only sigma y is acting, only tau xy is acting. This is tau yx. So we want to say what's happening to this element. So we got, finally I got the values from the results that I performed this test, torsion test. So I got the values of the shear stress on this particular plane, but I don't know what is the value of shear stresses here and sigma here, on infinite number of planes. Similarly, I got the values of sigma x, sigma y, and tau xy on a particular plane for this particular plane, but I don't know with respect to this plane, on a particular plane, what's this value of stresses on this plane, on this plane, on this plane, on this plane. So for that, your stress transformation is there. So if I say let's take any take any plane at an angle of theta with respect to vertical. Let's say for the derivation we are taking, let's say this is our new plane. We can say this is our desired plane. This is our desired plane. We want to say what's the value of stresses on this desired plane. So let's say this is theta with respect to vertical, anti-clockwise. So we can say this is the assumption that we are taking. So you have to keep it in your note, that theta with respect to vertical for derivation, theta with respect to vertical, and that's also anti-clockwise positive. We'd be taking anti-clockwise positive theta. So keep it a note, theta with respect to vertical and anti-clockwise positive. So you want to say what's the effect? We know that on a particular plane, on one plane, there is two shear stresses and one sigma acting, normal stress. So if I cut this section and I want to say what's happening on this segment, what's happening on the segment. So this was your sigma y, this was your sigma x, this was tau xy, and this was tau yx. Okay, now there would be on this particular plane, there would be some sigma x acting, we can say, we call it as a sigma x. So this is some plane. If I cut it in the 3D also, I can show it. So this was your 3D. If I cut at section in this fashion, so it would be somewhat this way. Let's say it's somewhat this way. You are saying on this particular plane, that I cut, what's the effect? What is stress? Because normal stress is perpendicular to the plane. Normal stress is perpendicular to the plane. So this is plane. I would say this is normal stress. This is normal stress on that particular plane. So sigma, I can name it this line as x dash. So I would say this is sigma x dash. I don't know the value of sigma x, so I would write it as a sigma x dash. So I would write it as sigma x dash. So this was your theta, anti-clockwise theta, and there would be some shear stress also on this plane. And if I say this is our tau xy dash, if I write it as in this way, let's say this is our line x dash line, and this is our line y dash line, then I would apply that summation of forces equals to 0. I can write summation fx dash equals to 0, summation fy dash equals to 0. I have to ensure that forces should be balanced in both directions. But these are not forces. If I say these are stresses, how can you convert that stress into force? So we have to multiply the stress by the area on which that particular stress is acting. So stress is a tensor. It acts on a particular plane. That particular plane should have some area A, so we can get the force value. So for that, you have to see so different stresses on what plane they are acting. So this was your cubic element. This was your cubic element. So let's say this was your cubic element. Let's say that this length is length. Let's say that when you cut this section, let's say the thickness of the element was t. We know that if it is a cube, I can say all the members are same of length, that a cube. Let's say this is some cuboid, thickness of t, and if I cut the section, let's name that this part. I can write it, this value is b, this value is a, and this is theta. So I can get the values. So this is say now I can say sigma x is acting on what particular plane. So if I say this is the particular plane on which sigma x is acting, this is sigma x perpendicular to that plane. So sigma x, I can write at the top that sigma x is acting on what particular plane. The area of that plane would be a, this is a into t. So sigma x is acting on a into t. And similarly, this was our tau xy. Let's write in this fashion. This was our tau xy. This was tau xy. This was tau xy. So it's acting also on the same plane. Tau xy is also acting on a into t, that parallel to that plane, a into t. Similarly, your normal stress sigma y, that's acting on this particular plane. That's I would write it as b into t. This is b into t. So I can write this area of some area of b into t. Sigma y is acting on b into t. Similarly, I can write your shear stress tau yx is also acting on the same plane that this was your tau xy. This was tau xy. It's acting on b into t. And when you cut the section, you would say sigma x dash is acting on what particular plane, and tau xy dash is acting on what particular plane. Let's when we cut the section, let's make it in this fashion now. See, I would name it as, say this length is a, this length is b. We have thickness t. So we know that this stress is acting in this. So I can convert this stress sigma x in the force. I can write sigma x into area into t, that a into t. This was a into t. Similarly, tau this was tau xy, this was tau xy. I can write it is acting on the plane, this plane. I can write it as A into T, area into T. Similarly, we have normal stress sigma y. I can write sigma y is acting on this length B and thickness of T. Similarly, tau yx is acting in this fashion, tau yx on this area B into T, tau yx B into T. Similarly, we have sigma x dash. So it's acting on this particular thickness is constant. Thickness is the constant value, but we don't know this value. Let's name it as C. So we can say from the triangle, right angle triangle, we have theta. We can write sine theta, that equals to perpendicular A, that's B by C. Cos theta is A by C, and similarly we have that tan theta, perpendicular by base, that's B by A. So we got the sine theta, cos theta, tan theta. So we can say C is acting, so your sigma x dash is acting perpendicular to this plane. So we can say the area of this plane is C into T. So you can write C into T. Similarly, I can say your shear stress tau xy dash is acting on that same particular plane, but it is parallel to that plane. So we can write tau xy dash C into T. So we got the forces. Now we have to resolve them in the x dash direction and y dash direction. Let's solve for the first for the x dash direction. Let's convert them into equivalent x dash and resolve them in the x dash direction. So this is our x dash direction. I would say here the stress is acting sigma x dash into it was acting on C into T, area of C into T. Isn't it? It was acting on C into T. Then we have, but the stresses are acting, say sigma y is acting in this plane, sigma y is acting on this plane. So we have to resolve those stresses along the x dash condition and y dash direction. So we have to resolve these stresses. Let's first resolve those stresses along those directions. So make one more diagram. We can say, let's say sigma y is acting in this direction. We would make four directions. Let's make 4 directions. So this is sigma x. I would write sigma x. Then after that, this is some sigma y. This is some y dash direction. On this plane, tau x y dash is acting. We can write into C into T, C into T. Is it okay? Tau x y dash C into T. Then we have 2 more directions. One is x and y. So if I write them by dashed line, let's say this is y direction and this is x direction. So along the x direction, we know along the x direction your sigma x is acting, sigma x, and area was A into T. Similarly, you are having in this direction tau yx is also acting, tau yx. So I would write tau yx, and area for that was B into T. Area was B into T for tau yx, B into T. Similarly, we have forces in the y direction, that was tau xy. This tau xy, it's along the y direction, and its area was that area into T, that A into T. Similarly, you had tau y, that sigma y is acting in the y direction, and the area was that B into T. So we're at sigma y B into T. So we got the forces along different direction. We had to resolve them in the x dash direction and y dash direction. So let's convert them into, let's resolve them along those 2 axes. So we know that theta, which one is the theta value? Do we know which one is the theta value? So we have from the vertical, you have theta anticlockwise. So from the vertical, you have theta anticlockwise. So this is theta, this is 90 minus theta. So this is theta. So This is 90 minus theta, this is theta, this is theta, this is 90 minus theta, so this is 90 minus theta. So we have to resolve them. So its component along the x dash direction would be, let's have that, we can write this is sigma y bt and 90 minus theta. 90 minus theta means the component would be sine theta, and also one more component is tau xy at into sine theta. So we got the components of these two stress forces along the x dash direction. Now we need to get of these two. So you have now these two forces also. So this is tau yx bt. So it's having theta with respect to some line. So we can say there is some value of stress that is tau yx bt into cos theta, or also some value of sigma x at into cos theta. So we got forces along the x dash direction. So we can balance the stresses along the x dash direction. Let's write that sigma x dash ct, that equals to the sum of all those values, sigma y bt sine theta plus tau xy at sine theta plus tau yx bt cos theta plus sigma x at cos theta. So we know that the value of, if I divide that, since t is common in every term, so we can ignore the value of t. But so if I divide that, see we have that. We want to say what's the value of sigma x only. That's our desired thing is that get the stresses along that particular plane, sigma x and tau x. This is our goal to get. We want to get the value of sigma x from the known values of sigma y, tau xy. We know that we have sigma y known, sigma x known, and tau yx known, but we only need to get the value of sigma x dash. So if we divide that divide every term by value of c, so we can say you would get here, say b by c, a by c, b by c. So we want to say what's the value of b by c and a by c from that triangle. So b by c is sine theta and a by c is cos theta. So b by c sine theta, b by c is sine theta. So if I write it as in this fashion, that tau x dash equals to sigma y, b by c becomes sine theta. So your sine theta becomes sine theta into sine theta becomes sine theta square, sine square theta plus tau xy. Similarly, a by c becomes cos theta. So I can write cos theta sine theta plus tau yx, b by c was sine theta. So I can write sine theta cos theta. Similarly, I can write here sigma x, a by t was cos theta. So I can write cos square theta. So I got the result. But from the complementary shear stresses, we know that sigma y equals to that tau yx equals to tau xy. So I can write sigma y sine square theta plus sigma x cos square theta plus 2 times tau xy sine theta cos theta. This is the general value that you got, general result. So if you want to make it more simplify in terms of linear function of that theta, I can say from the results we know that sigma x cos square theta is 1 minus cos 2 theta by 2, and sigma y into sine theta is 1 plus cos 2 theta by 2. Is it? Cos square theta is 1 plus cos 2 theta, and sigma y sine square theta is 1 minus cos 2 theta by 2. Similarly, we have plus 2 times. Can you get the value of sine theta cos theta? We know that sine 2 theta, that's 2i sine theta cos theta. So we can write tau xy sine 2 theta. So when you get the solve it, we can say sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sine 2 theta. That's your sigma normal stress along x direction at any particular plane that equals to this value. So we can say this is valid for all theta. By valuing, so we can say sigma x dash is a function of theta. It is a function of theta. By rotating that particular plane, I want to say this was our main plane. We know that here the sigma x, sigma y, we know that sigma x, sigma y, tau xy is acting. We know that these three values we know. We know these three values. Now I want to say at particular theta, 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 get the values of stresses, sigma x dash. This is the transformation of stresses. So similarly, we want to get tau xy dash. So we have to balance those forces along the y direction also, y dash direction also. So we got one result, that sigma x dash plus sigma y dash. Sigma x dash we got. So let's balance now. Let's balance now along the that y dash direction. Let's convert the forces into in the y direction. Resolve the forces in the y direction. So this part is over. 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 And we have to say let's resolve the forces in this direction now in this direction. Let's wait for a while. See, you have tau xy acting, so you have to get its effect on a particular value of theta. So on a particular plane, so you resolve that. So we can write this is sigma xy at into cos theta, and this one is sigma y. First one was tau xy. So this one is sigma y bt into cos theta, and we have these two forces acting along this direction. So we can resolve those two forces in this direction. So this is tau yx. This is tau yx bt and sine theta, and or we can write cos 90 minus theta, that is sine theta, and similarly we can write sigma x at sine theta. So we got the forces. Now you have to balance those. Let's write tau xy dash ct in one direction. Yeah, then you have to transfer these two. So we can write minus tau yx bt sine theta and minus sigma x at sine theta. Then you have those two more forces in that upward x dash upward y dash direction. So we can write those two also. So we have plus tau xy at cos theta plus sigma y bt cos theta. So you need to now divide by that d and c. We know that b by c was sine theta. From that triangle, this was AB, this was ABC theta. So we can write tau xy dash, that equals to minus times tau yx. B by c was sine theta, so we can write sine square theta. Sine square theta. B by t. Let's see one more time. What was the value of b by c? B by c sine theta. So let's say what's going on. So we can write sigma x. A by c was cos theta. We can write cos theta sine theta plus tau xy. What's the value of a by c? That's a by c equals to cos theta. We can say cos square theta. We can say cos square theta. Similarly, we have the final value of sigma y. B by c, that's equals to b by c equals to sine theta. So we can write sine theta cos theta, sine theta cos theta. So we got this. Now we want to say, let's simplify it to see what's the final result. So we got tau xy dash, that equals to sigma x. So we know that tau yx equals to tau xy. If I take that common, I can say this is tau xy, and we have cos square theta minus sine square theta. Then we have one more thing. Then we have plus sigma y minus sigma x sine theta cos theta. Sine theta cos theta. So now how can you solve this further? Yeah. If I know the value that this is tau xy, cos square theta equals to 1 plus cos 2 theta by 2. Isn't it? Let me check the value of that. Let's wait, and I would see what's the value of tau x, that cos square theta. Value of cos square theta. Cos square theta. One minus cos square theta is 1 plus cos 2 theta. Yeah, 1 plus cos 2 theta by 2. So cos square theta is 1 plus cos 2 theta by 2. Then we have minus. Then we have minus 1 minus cos 2 theta by 2. Sine square theta equals 1 minus cos 2 theta by 2. So we got these two values. Then we write sigma y minus sigma x. Do we know what's sine 2 theta? Okay, right. It is sine 2 theta by 2. You know that sine 2 theta is 2i sine theta cos theta. So we can write in this fashion also. So let's simplify it one more step also. We can say how much value it's coming. So we can see if something gets cancelled here. If I say 1 by 2 and 1 by 2, 1 by 2, 1 by 2 minus times. So I would say tau xy cos 2 theta 2 times and divided by 2. That means cos 2 theta. Cos 2 theta. Cos 2 theta. You're left with cos 2 theta. Tau xy cos 2 theta plus, if I write it in terms of this one, sigma x minus sigma y by 2 sine 2 theta. So I got the result that tau xy dash, that equals to sigma minus times sigma x minus sigma y by 2 sine 2 theta plus tau xy cos 2 theta. So these are the two results that we got. Now the thing is that you got stresses at any x, at any particular plane, shear stress and normal stress. But what about the maximum? What should be the value of maximum normal stress maximum, and what should be the value of tau shear stress maximum? On what particular plane shear stress is maximum, and on what particular plane your normal stress is maximum? So for that we can write next topic, that's location, right? Location of sigma max and tau max. So we have these results. So we write those results. Let's write those results here. So we have to say what's the value of maximum, what should be the value of that sigma max on what particular plane with respect to the given stresses on that particular plane that you have, on what particular plane with respect to that plane which we have given, the stresses would be maximum. Let's calculate the sigma max. For we can write for sigma max to be maximum, for sigma x dash to be maximum, that means to be it is as a sigma max. So we can say we can differentiate it d sigma x dash, differentiation of that sigma x with respect to the theta, that should be 0 at one particular plane, so we can get the location. So we have that d by d theta of sigma x dash, that's sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sine 2 theta. So we want the differentiation, we want to minimize it with respect to the theta. So let's calculate that. We know that for this one it would be 0. We can write 0 plus sigma x minus sigma y by 2. Differentiation of cos 2 theta is minus sine 2 theta, and you divide by 2. Then plus tau xy cos 2 theta divided by 2. That equals to 0. So let's write the that theta in one side. We can say sine 2 theta by cos 2 theta equals to 2 times tau xy sigma x minus sigma y, that equals to tan 2 theta. So we got the value of theta, that at a particular value of tan 2 theta you have that sigma to be maximum. So we can name it as, now we can say tan 2 theta, but we can keep it as we can write it as a p. So we can have 2 times tau xy sigma x minus sigma y. What's the value of what this p means? This p means that, let's say what this p means. So we got this value of p. Let's say on this plane, on this particular plane, we want to say what is the value of shear stress. Then I will tell you what this p means. Let's convert this in terms of triangle, right angle triangle. You have tan 2 theta here, 2 theta p, and you have perpendicular by base. Let's write it as tau xy. Let's write this one as sigma x minus sigma y by 2. So there is some resultant of that. We can write it as tau xy whole square plus sigma x minus sigma y by 2 whole square. Let's say this is some resultant value of r. We can say, now we can write, so if you want to say let's write the tau xy equation at this particular plane at theta p location. I want to say what's the value of shear stress. I want to say what's the value of shear stress on that particular plane where the normal stress is maximum. Let's write that equation that we have. So we would write the same equation here, tau xy dash. So we can write minus times sigma x minus sigma y by 2, and you have to write sine 2 theta. Can you get the value of sine 2 theta here? From this triangle, can you get the value of sine 2 theta? Now your theta becomes theta p, sine 2 theta p. Can you get the value of sine 2 theta p? That's perpendicular by base, perpendicular by hypotenuse. So tau xy by some value of r. Similarly, you have cos 2 theta p. That is some value of sigma x minus sigma y by 2, and you have divided by r, perpendicular by hypotenuse. So we got the value of sine 2 theta and cos 2 theta. So we can write this into some value of sine 2 theta. That sine 2 theta equals to tau xy by r. Then you have plus tau xy, and you have to write now cos 2 theta. The value of cos 2 theta is sigma x minus sigma y by 2 and 1 by r. So if you see your tau xy becomes, so tau xy at the rate of theta p, that equals to 0. We can say on maximum normal stress plane, your shear stress is 0, your tau is 0. That's what we call it as principal plane. That plane on which normal stress is 0, we call it as a principal plane. And so we can say on the principal plane only normal stress is acting, only sigma is acting, no shear stress is acting, no shear stress is acting. So your principal plane is that sigma is there, but your tau is 0. This is the principal plane. That's why I write that value of p. So but we know that there can be from this equation that tan 2 theta p for particular value of tan 2 tau xy sigma x minus sigma y, we can have two values of tan theta. We can have two values. One can be at, we know that tan theta, we know that tan theta equals to tan 180 plus theta. Do we know that? So for the same value of 2 tau xy by sigma x minus sigma y, we can have two values of theta. That's possible only when the two theta are separated by 180 degree. So if I write that, let's say this was tan theta p1, I can write that 2 theta p1 at that particular location, and if you add 180 degree, so we can get one more theta p2. So I can say theta p1 is so difference of the two principal plane. I can say there are two principal planes perpendicular to each other. They are separated by angle of 90 degree. So as we know that if you have two principal planes, if you have two planes that here sigma x is acting, sigma y is acting. So one particular plane you have, then perpendicular to that, normal to that, you have one more plane on which that sigma is acting, different sigma is acting. So if the two planes are perpendicular to each other such that here tau is 0, and on this plane also tau is 0, so we can call them as two principal planes in plane stress condition. We are not saying that tau z is sigma z is also. We say that sigma z is 0, so we call it as plane stress condition. In that we have two principal planes. Where tau is 0. So we got the two. Look, we can if you substitute the value, of that in this equation tau xy, that sigma xy dash, you know that if you substitute here, the value of theta equals to 90 plus theta, and if you substitute here 90 plus theta, you can get the same equation, but with a sign that this value becomes negative and this value becomes negative. So we can call as sigma y dash. See, when you derive that, we say we got this plane. We say that this is the plane on which we want to find that particular value of sigma. So we say that this is on that particular plane perpendicular, that there is some normal stress that is called as sigma x dash. But if I say, if we have one more plane that's perpendicular to this plane, on that plane there is some stress acting, that's called as sigma y dash. To calculate the stresses on that particular plane, you have to rotate the element by 90 plus theta. You have to check the value of stress at 90 plus theta with respect to that vertical, anti-clockwise, 90 plus theta. Then you substitute the value of 90 plus theta here, and you get the results that there is negative. So finally we got that shear stress is 0 at the plane where your sigma x, that normal stress is maximum, that we call as principal plane. So finally we got the result that you need to keep in mind, that tan 2 theta p equals to 2 tau xy by sigma x minus sigma y. Also remember this triangle, and we can say we have two principal planes that are separated by angle of 90 degree. We got this one also, and we have that on that principal plane we have sigma acting, but tau is 0 there. That means no shear stress is acting there. Now we want to say that normal stress is over. Now we want to say what's the value of maximum. So this one is over. Now the thing is, get the value of location of tau max. So we write tau max. Want to get the value of tau max now. Let's get the value of tau max. So we can write for tau to be maximum, for tau xy dash to be maximum, we can write dou by dou theta of tau xy dash equals to 0. So we can write dou by dou theta of that equation we have, that minus times sigma x minus sigma y by 2, and cos 2 theta, no, sine 2 theta plus tau xy cos 2 theta, that equals to 0. So you solve it. So we can write minus times sigma x minus sigma y by 2. Differentiation of sine 2 theta is cos 2 theta divided by 2 plus tau xy, and minus times sine 2 theta divided by 2 equals to 0. So we got the value that sine 2 theta by if you let's keep it now in this fashion, that it has become positive. So we can write cos 2 theta, that tan 2 theta equals to that sigma x minus sigma y by 2, and you divide by tau xy, and you have also negative sign also there outside. So we got this result. So here we can keep it as tan 2 theta s means shear stress. So we can get the value of particular shear stress plane, where shear stress is maximum, tau max plane. So if I make the triangle for this one, let's make the triangle for this one, that tan 2 theta s, they can write this is 2 theta s. I can say this one is sigma x minus sigma y by 2, and we have this one tau xy, and there is some resultant of that sigma x minus sigma y by 2, and it's minus times that it would finally become positive, and we have tau xy whole square. Let's call it as some resultant R. Now want to say what's the value of maximum shear stress. So want to say what's the value of maximum shear stress. So from this we can get the value of maximum shear stress. Let's call it as tau max. So we can write minus times sigma x minus sigma y by 2 sine 2 theta. From here we can say sine 2 theta theta s, that equals to minus times sigma x minus sigma y by 2, and you have hypotenuse of r. Similarly you have cos 2 theta s, that is tau xy by r. So if you substitute here, you can keep it that that sine 2 theta, this sine 2 theta you have to multiply here, minus times sigma x minus sigma y by 2 into r, then plus tau xy, then you have cos 2 theta, that's tau xy by r. We got some value that's sigma x minus sigma y whole square by 2 whole square, and you divide by r plus let's keep the r outside because r is both common in both the terms. So I can say tau xy whole square, but the value of r, actually the value of r equals to, so the value of r is that root of this value, the same value which we are at the top. This is the same value here, but it has root. So if you have, say we have 2 by root 2, that equals to root 2. So we can say tau max equals to, can we say that tau max equals to root of sigma x minus sigma y by 2 whole square plus tau xy whole square. Can we say that? So we got the value of tau max at some particular value of theta, that is theta s, that we calculated tan 2 theta s here. So want to say, now we got the value of tau max. Want to say what's the value of normal stress. We want to say what's the value of normal stress. Want to say what is the value of normal stress on that particular plane where the shear stress is maximum. Want to say what's the value of normal stress on that particular plane where shear stress is maximum. So we got the value of shear stress and the location. Want to say what's the value of normal stress at that particular location. Let's write that. We know that sigma x dash. Let's write that sigma x dash equals to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2. Then we have cos 2 theta. Cos 2 theta here from the triangle cos 2 theta, that is tau xy by r. Tau xy by r. Tau xy by r. Then plus we have tau xy sine 2 theta. Sine 2 theta. Sine 2 theta. So sine 2 theta is minus times. So we can write into minus times sigma x minus sigma y by 2 into r, which is our sigma max. So we say sigma x plus sigma y by 2. Say in this part we have this value positive, and the same value is here also, but it is negative sign here. So finally you get value of sigma x dash equals to this one. Do we got this? Sigma x dash equals to sigma x plus sigma y by 2. So similarly, you would get at 90 degree to this plane, sigma x dash, you can get sigma y dash also equals to sigma x plus sigma y by 2. That's the average of the two normal stresses acting on the plane. So the conclusion is that on tau max, on principal plane, on theta p plane, your sigma x dash becomes sigma max. It becomes sigma max. You have two principal planes. One is theta p1, next one is your theta p2. On theta p1 we have sigma max, and on next principal plane we have sigma min. They are separated by 90 degree angle. They are separated by 90 degree. And first principal plane we call it as sigma 1. Minimum principal plane we call it as sigma 2, and we call it as major principal plane. Yeah, major principal stress, and we call it this one as a minor principal stress, or we call it as so the plane on which this acts, we call this as principal plane, major principal plane, the plane on which this acts, we call this that as major principal plane, and similarly this plane on which minor principal stress acts, we call that as minor principal plane, So we know that on these two theta planes, these two theta p's, we have tau equals to 0. Shear stress is 0 on these two principal planes. So then after that we have tau max plane. Tau max plane was at theta shear 1, theta shear 2. If you say see, you have this note, you write that note also, that on two different values of, we know that we got the value of tan to theta s equals to minus times sigma x minus sigma y by 2 into divided by r divided by tau xy. So we can have two values of tan to theta s. So both, but say they are separated by 90 degree. So they are separated by 90 degrees. Say one is theta s1, next one is your theta s2. They are separated by 90 degree angle. But the thing is, both will have same tau max. Both have same value of tau max, and both have same value of normal stress acting. So on the, so you can say on the maximum on the maximum shear stress plane, on tau max plane, we have normal stress sigma x equals to sigma y, that equals to actually the given sigma जो आपका sigma value दिया हुआ था, sigma x plus sigma y by 2. Both values are same. That is equals to that average of the two values, sigma x plus sigma y by 2. Okay, we have reached it. So we have reached to where, let's say now we are on a point that, let's say you were having an element. This was your element. You want to say what's the stresses on this plane making angle 40 with respect to the horizontal plane. With respect to this line, it's making 40 degree. You want to say what should be the value of theta? What should be the value of theta for the calculation? If you want to use those equations, sigma x dash x y dash, in those equations, what should be the value of theta you have to put? Question is saying get the value of stresses, on this plane which is making 40 degree with respect to this line. So if you want to say what should be the value of theta, let's make it in the fashion that we have in that derivation. Let's say this is, we know that from the horizontal you have 40, but we don't care about the horizontal. We have taken the in the derivation we take theta with respect to vertical, and that was also anti-clockwise positive. That anti-clockwise was positive. Anti-clockwise was positive. So anti-clockwise is positive. So if you take theta from vertical, anti-clockwise positive. So theta becomes, this is 90, this is 40, this is then 90 minus 40, that is 50. So your theta becomes 50 degree. Similarly, you have one more. Let's take one more stress element. On that you already know there is some sigma y, sigma x, and tau xy. You want to say what's the value of stresses on a plane that's making 120 degree clockwise with respect to horizontal axis. So let's say with respect to horizontal, it's making angle of 120 degree. So get the value of theta. So let's make that in a fashion that it cuts the vertical axis. We want to cut the vertical axis to get the clear picture. So our goal is to cut the vertical axis. Let's make the same line such that it cuts the vertical axis. So we can say, let's say this was your, from this x-axis, from the x-axis you are having a theta of 120. So you are having 120 theta. So what's the value of theta for us? So our theta with respect to vertical, that is this value, theta. So this is our theta. Theta equals to, so if this is 120, up to this part it is 90, then the left part, remaining part from this part to this part, that is 30 degree. If it is 30 degree out of the total, we were having a total of 180. So 30 degree has been eaten by this line. So we can say you are left with 180 minus 30. So we can say 150 is your theta. 150 is your theta. Let's take one more. Let's say that 150, we're done with this one. Let's say we got the stress element. Now we're saying we have two planes such that they make an angle of 30 degree with respect to the vertical. So this is making angle of 30 degree, and this one is also making angle of 30 degree with respect to the vertical. So what's the value of theta? Say this is line AB, this is line CD. Get the value of line theta for AB and get the value of theta CD. What should be the value of theta for the calculations? Let's say for the AB. Are both the same? Are both theta same? Actually, they are not the same. See, for the AB, you have to write anti-clockwise is positive, so you have to write 30 positive. Similarly, this one is anti-clockwise, so you have to write minus 30. You have to write minus 30 for line CD or plane CD. This is CD plane. If you want to find the stresses on the plane CD, you have to write the theta equals to minus times 30 with respect to vertical, or you have to go from the vertical in the anti-clockwise direction and get the value of this one. So this value becomes equals to actually this is 180 minus 30, that's 150, or you can say plus 150. Minus 30 or 150 plus. So let's take one problem that We got the stresses on a particular element. Stress element is given in this fashion that you have tau xy. This is 2. Here it's also 2. Tau xy equals to tau xy, tau yx. So and a normal stress of sigma x equals to 5, and sigma y that equals to, that's compressive sigma y. Sigma y is compressive, 2 megapascal. So sigma y is compressive. Rest all other are, say, sigma x is tensile, sigma y is compressive. So get the value of stresses on a particular plane that's called as AB, and one more plane is there that's called as CD. So we have one plane that's making AB, that's making an angle of 60 degree with respect to horizontal. So we have 60 degree here, and next plane is CD, that is perpendicular to plane AB. So we can say CD is perpendicular to plane AB, CD plane perpendicular to AB plane. So firstly we can say calculate for the plane AB. Let's calculate for the plane AB. So the line is in this fashion. We want to make it cut the vertical axis that we have reference line. So this is our reference line. We want to cut the AB we want to cut the reference line by that line AB. So this is our AB line. I can say this is our plane AB. It's making an angle of 60 degree. So your theta becomes, so this is our theta anti-clockwise. So we can write theta equals to 30 degree. So you can calculate the stresses on that particular element. Say the stresses is sigma x dash and tau is tau xy dash. So you can write sigma x dash equals to sigma x plus sigma y by 2. We have that sigma x plus sigma y by 2. So we write those values. So we can say sigma x is positive 5 tensile, sigma y is negative -2, and tau xy is 2 positive. In the derivation we have assumed that tau yx was in this fashion, and sigma y was upwards, sigma x was this way, and tau y and sigma x dash we kept in this direction. We kept a sigma x dash positive, and tau xy dash in this direction positive. So these were the sign conventions that we followed during the derivation. So you have to note them, which values are positive. These directions you have to keep that these are positive. So we got the value that we can say sigma x dash equals to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sine 2 theta. So you can get the values of sigma x dash. So we got the values of sigma x dash, some value. Similarly, you can get the value of tau xy dash on that plane AB. This is the calculations for plane AB. So you can get sigma minus times sigma x minus sigma y by 2 cos 2 sine 2 theta plus tau xy cos 2 theta cos 60. So you got the values of sigma that stresses on that particular plane AB. If you want to say what's the stress values on the plane CD, for that you need to get the value of theta. You need to get the value of theta. Say that now the next plane would be this one. This is the CD plane. This is CD plane. So it's making an angle of this one. This is our theta now. So we want to get this value theta. We can say, let's say if this was making 30 degree with respect to vertical, we can say this will make this 30 degree, it would make this 30 degree plus it would make this 90 degree also. Can we say that? So your theta can become 90 plus 30, 120. So you substitute the value of 120 here for the next plane. You substitute the value of now if I want to calculate for BC plane, I can calculate here. You substitute the value of here 2 into theta, here also 2 into theta, here 2 into theta, and 2 into theta. Rest is calculation same. We just want to, we are just checking the effect of these three stresses on different planes, infinite number of planes, with respect to this given reference plane. We want to say how these stresses have been transformed on different planes with respect to this given plane. So we got this one also. We got this one also. We got this one also. One concept is there, that is stress invariance. Stress invariance. We have stress invariance. Stress invariance. Stress invariance. We have the equation that sigma x dash equals to sigma x minus sigma y by 2 plus sigma x. We have that sigma x minus sigma y by 2 cos 2 theta plus tau xy sine 2 theta. Now, if we want to say what's the value of sigma y dash, that would be this was our that plane that we cut, and on that perpendicular to that plane we were having sigma x dash. So similarly we have next plane, that's sigma y, that's next plane would be somewhat that's perpendicular to the given plane, that's making 90 degrees to that plane on which sigma y is acting, sigma y dash is acting. So from the reference that we take, that vertical, from the vertical it's making an angle of, this plane is making an angle of 90 plus theta, 90 plus theta. So if you substitute 90 plus theta in this equation, so you can get the value of sigma y dash, that equals to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta 2 theta. Theta is 90 plus theta, and similarly tau xy 2 90 plus theta sine 90 plus theta, sine of 2 times 90 plus theta. And when you substitute values, you would get the value of sigma y dash equals to sigma x plus sigma y by 2 minus sigma x minus sigma y by 2 cos 2 theta minus tau xy sine 2 theta. So when you add, if you add sigma x dash plus sigma y dash, if you add these two, you can say, when you add these two equations, this one and this one, you would get sigma x dash plus sigma y dash equals to, see, this is 1 times and this is 1 times, you adding them, so we get net value of sigma x plus sigma y by 2. And here in this part you have positive this term, and here you have negative this term, so it gets cancelled. And similarly you have negative this term, you have positive this term, so this is also getting cancelled. So we get this relation that stresses on two perpendicular planes. So we can say if you are having stresses, this was your sigma x and this was your sigma y. So if you add that sigma x plus sigma y, now you cut any plane, you want to say let's have the stresses, let's have the sigma x on this particular plane. Let me calculate the stresses on sigma x plane. Let's say the value comes out to be equals to 5. Let's say the sigma x plus sigma y was such that sigma x was 5, sigma x was 10, so I can write 10 plus 5 equals 15. Final value should be 15. Let's say sigma x dash came out to be 8. Sigma x dash came out to be 8. Let's say now there's one more plane perpendicular to this plane. I would say that is this plane. So there is some stress acting on this particular plane, that's sigma y dash, that has to be equals to 8 plus 7. That's 8. It has to be equals to 7. That's what is called a stress invariance. Stress invariance. That we can write in plane stress. It's valid. We have studied all this derivation and all the stuff for the plane stress condition. Plane stress condition, that tau z is 0. Plane stress condition, that is tau z is 0. Yeah, sigma z is 0, tau x z is 0, tau y z is 0. These three you have to say these are 0. Then we say that summation of normal stresses on cubic element of material is independent of orientation of element. So it's a statement that summation of normal stresses onto mutually perpendicular planes onto perpendicular planes are is not function of theta, is not function of, or we can say it is independent of orientation. It is independent of orientation of those two perpendicular planes. That's the concept of stress invariance. So if you get that directly, you can say if you got sigma x dash from the calculation, that formula we know, if you get sigma x dash and you already know what's the value of sigma y, and sigma x, sigma y you know already on that particular segment, and sigma x you also know, so you can directly calculate what's the value of sigma y dash. That is the sigma x plus sigma y minus sigma x dash. So this is also over. Sigma x stress invariance concept is also over. We also find maximum theta planes. We also got this one, tau max at theta share. So we also got tau max also. So yeah, we forgot one thing, that when we derive that theta principal plane, when we derive that location of theta, location of sigma max plane, then we got that theta p1 and theta p2. So we got that tan 2 theta p1 or theta p equals to 2 tau xy by sigma x minus sigma y. We forgot to substitute that a particular value of theta in the sigma x dash condition. So we were having that, we forgot to substitute the value of theta there. So this was our triangle, theta p, this was tau xy, this was sigma x minus sigma y by 2. This was some resultant value, so this is resultant root of this one, so there is some resultant. If I write that equation, that sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta, that is perpendicular base by hypotenuse. So I can write sigma x minus sigma y by 2, and there's some value of r, then plus tau xy sine 2 theta, sine 2 theta is equals to tau xy by r. So I got value of sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 . So there is common term is r between the two, so I can say this is square. Similarly, this one, this is also tau xy whole square. But if I see what's the value of r, that equals to tau xy whole square plus sigma x minus sigma y by 2 whole square root. Is this hypotenuse? This is the hypotenuse. So already we said that 2 by root 2 equals to root 2. Similarly, this value of r is also that, this one, which is in the bracket. So we can say we got the value of sigma. So we can call it now. We can call it as sigma x dash. We can call it as sigma max. Can call it as sigma max. Can we call it as sigma max? So we can call it as sigma max. So you have that sigma x plus sigma y by 2 plus that root of r. That's root of r. That's this one, tau xy whole square plus sigma x minus sigma y by 2 whole square. So we can say tau max, yeah, we can say sigma max, maximum principal plane, we call it that as, we name it that as sigma 1. So we can say sigma x plus sigma y by 2 plus root of sigma x minus sigma y by 2 whole square plus tau xy whole square. This is our standard result. If we know that when we calculated the location of the maximum theta shear stress plane, then we got that tan 2 theta s, and from that we got the value of tau max. That was also equals to this value. So we can say sigma 1 equals to sigma x plus sigma y by 2 plus tau max. This is also one conclusion that you have to remember. And once we got the sigma 1, Once you got the value of sigma 1, you can get the value of sigma 2 by substituting theta. Theta changes to theta plus 90. So theta p1 was this one. So theta p2 would become theta p1 plus 90. So by substituting the value of theta to theta plus 90 in the equation here, you have to substitute the value of theta to 90 plus theta 2. We can say 90 plus 2 theta p, or we can say this changes to 2 theta p changes to 180 plus some theta 2 theta p, and you substitute that, you can get the value that sigma 2 is sigma x plus sigma y by 2 minus times tau max. This one, there we can say in a general way, we can say sigma 1 or sigma 2, that is plus minus. You can say here plus minus. If you want to get 1, you have to add here 1 plus. If you want to get sigma 2, you can say keep it negative sign here. So there's a conclusion then. When you add sigma 1 plus sigma 2, you get a value that tau max finally becomes equals to sigma 1, difference of the two principal planes, sigma 1 minus sigma 2 by 2. Yeah, when you subtract areas. So you get a value of tau max equals to sigma 1 minus sigma 2 by 2. This is one more conclusion. Now we have one more condition that we call it as absolute maximum, tau max absolute. We want to say what's the maximum shear stress absolute. So we know that sigma max, tau max equals to, from this result, we know that tau max equals to sigma 1 minus sigma 2 by 2. If I say sigma 1 minus sigma 2 by 2, let's say sigma 1 can be positive or negative, but sigma 1 means it's a value of that's positive, that its magnitude is maximum, that maximum magnitude is having it. It's having maximum magnitude. It can be tensile or compressive. It can be compressive or tensile. So it depends on the value of sigma 1 and sigma 2. So so if you want to say tau max in plane, firstly if we say tau max in plane, and for plane stress condition means, you know that sigma 3 is 0, that means sigma z is 0, that is sigma 3 is 0. For that you can say sigma 1 minus sigma 2 by 2, comma sigma 1 minus 0 by 2, comma sigma 2 minus 0 by 2. Out of these, the magnitude of the maximum of these three, that give me tau maximum, overall tau maximum. If you want to say if it is directly saying what get the value of tau max, it's generally saying get in plane tau max. It's not saying get tau max absolute. If it's mentioning that get tau max absolute, then you have to see, you have to go with this condition, that this one and this one. If it is saying tau max absolute, it's saying the tau max absolute, then you have to see what's the value of sigma 3 also. So final conclusion would be like this one, that for tau max in plane, you only solve sigma 1 minus sigma 2 by 2 magnitude. If it is saying tau max absolute, that means out of all those three stresses, sigma 1, sigma 2, sigma 3, get the value of tau max such that it is maximum of the three, maximum of sigma 1 minus sigma 2 by 2, sigma 1 minus sigma 3 by 2, and sigma 2 minus sigma 3 by 2. So if then the sigma 3 is 0, then accordingly you can get the value of still maximum, which one should be maximum. It depends on the negative and positive sign of those stresses. Sometimes sigma 1 and sigma 2 both are positive. Let's say it is 100 and this is 50. If you write 100 minus 50 by 2, that's 25. So, but if the stress sigma 1 is 100 and sigma 2 is minus 50, you write 100 minus of minus 50, then tau max becomes 75. So you have to see the sign also, and you have to see with respect to that, you got two values, that 100. See, you got two values here. One you got firstly you got 100 minus 50, that was 25, you got one value of 25, you got one value of 75. And third one is that if you say 100 minus 0 by 2, that's because sigma 3 is 0. If you are calculating this part also, you get a value of 50. If you are saying 50 minus 0 by 2, that's 50, 25. So you got four values, that 25, 50, 25, 75. You want to see what the question is asking. Either it's asking in terms of absolute value, or it is saying in the plane I am asking, the particular plane, that xy plane only. You have to then say sigma 1 minus sigma 2 by 2. So this was all from this lecture, derivation and a little bit of concepts. Next lecture would be on the other parts of that stress transformation and some problems associated with that. Thank you for watching our lecture on stress transformation.